In this video, I'm going to talk about a solution to linear time invariant system. So this video and next video talk about solution to linear time system, and this video will focus on linear time invariant system. So for linear time invariant system, we're talking about the standard form, which is given by x dot t is axt plus but yt is equal to cxt plus dut. We also call this the state space representation. So for linear time invariant system, we here assume that this A and B and C and D, those four matrices, they are constant. They do not change over time. If A, B, and C, D, they change over time, we call this linear time invariant system. So we'll talk about solution in the next video. So briefly speaking, the analytical solution to the linear time invariant system can be written in this way. So you can find the solution to the linear time invariant system, you can find the exact solution to the linear time invariant system, which is given by xt, which is e to the a sub t, and time x0. So here x0, I want to emphasize over here, x0 is right up here. X0 is initial state, okay, or initial condition, and the EAT time x0 plus integration from 0 to t e to the a time t minus tau and b u tau d tau. Okay, y of t is c. You basically see xt time plus dut, or since we already have the xt, so it's just c time xt, so c time eat e to the a time t time x0, again x0 is in this state, plus c times 0t e to the a t minus tau b u tau d tau. So these first two terms is just c times xt and plus dut. So that's it. That's solution of y of t. So sometimes people tend to move the c inside because you can compute sometimes c time eat minus tau time bu tau. This can simplify the whole process a little bit. If C has a number of zeros, a lot of those entries in C are zeros, so you can move C inside to simplify the computation. So here we can see we have one specific function here, which is e to the a sub t. So this is defined by, or you can have e time e to the a t minus tau. That's the same. You can write the same way, but the difference is that you move from t to t minus tau. Other than that, the computation will be fairly the same. So e to the a time t can be computed by this. So this is what's the definition of e to the a time t, which is equal to identity plus at squared divided by 2 factorial plus at to the cube divided by 3 factorial, so on and so forth. You can sort of write this as the summation from from 0 to infinity of this form, which is at to the i's power divided by i's factorial. Okay, this is actually the same as e to a general scale, e to the t, for example. It's just for a scalar case. This is a times t. This is a matrix. So this is a matrix. Okay, so this, you can consider this as a scalar case. This is also 1 plus t squared plus 2 factorial plus t to the cube divided by 3 factorial plus so on so on. It just replaces t by a times t. That's it. Similarly, if this is e to the a minus t times t minus tau, you just replace at by a to the t minus tau, everything like that. So you just replace this by this guy. So it will be you can compute the e to the a times t minus tau. Okay. Also, we do have this analytical solution. So a lot of times we want to find the exact solution to a linear time invariant system. What I mean by that is you still have to compute all this e to the a sub t. You compute all the integration, so this can be very complex. So how do I find an exact solution to a linear time invariant system? Of course, you can use this one by finding out all the exponential of the a times t, and then you do the the product by e to the a dot t times x0, and you do the integration. You compute that, you can find a solution. Of course, that's one way. The other way is also the linear. We can use a Laplace transform and inverse Laplace transform. A lot of time that way can be a little easier. Okay. All right. So typically there are two approaches that we can use to find the exact solution to the linear time invariant system. So this is the analytical form. Okay, but the exact solution is for if I give you A, B, C, D for specific values, how do I find a solution? Okay, exact solution to that. So the first approach is you can use a direct method, like I mentioned over here, by using an analytical solution, but you have to compute what is the e to the a sub t for a specific A matrix. Of course, when you have to compute that, you compute also e to the a time t minus tau. Okay, then you do the product, do the integration, so on and so forth to find a solution. So general idea is you give you a, so you can compute e to the a sub t. Okay, based on this definition. Of course, this can be complex. So a lot of times to compute this e to the a sub t, you can use the similarity transformation that I mentioned in the mathematical background part. What we do is write a into the p inverse lambda p. So hopefully lambda is diagonal. So here let's assume lambda is diagonal. So e to the a sub t is just equal to p inverse e lambda t times p, which is p inverse e to the lambda 1t, lambda 2t, so on and so on. Assuming that my lambda I, there's eigenvalues, okay, and time p. So that's it. So you can write this form exactly as this form, okay. So once you figure that out, of course you can also figure out this way. The only difference is here is once you have t minus tau over here, so this t become t minus tau. That's it. So that's the difference, okay. So once you figure that one, you can compute integration from 0 to t e a t minus tau b u tau d tau, which is exactly what I mentioned right over here. Okay. Then you can figure out the solution of xt, because you already figured out this guy. If you know initial condition, you already figured out this one. So yeah, you can find this xt. So once you figure out xt, then you can plug in this yt cxt plus dut. You can find the solution. Okay. So that's where you can find the solution to the linear time invariant system exact way using direct approach. Another approach that you could consider is the Laplace transform and inverse Laplace transform. So it's indirect method, doesn't use the direct solution as the analytical solution, but you can still find the exact solution. Okay, so sometimes this approach may be a little bit easier to use. Okay. So here's the idea how to use a Laplace transform and inverse Laplace transform. Since this direct method approach is pretty straightforward, and I won't give an example for the Laplace transform and inverse Laplace transform. I'll give an example showing how to do that. Okay. So here example, I give you the linear time invariant system, which is x dot t is equal to 0, negative 1, 1, negative 2. So here this is, you can consider this is my A matrix. Okay, this is my B matrix. This is my C matrix, and this is my D. Of course, D is not a matrix, it's just a number. So, of course, given this condition x0 is 1, 1, and I also give input the use of t is 1. Okay. So to use the Laplace transform and inverse Laplace transform to find the solution, we first apply Laplace transform to both equations, including the x dot t and the yt. Okay. So for the x dot t, the first equation, we apply Laplace transform both sides, okay, which is just given by first this one, okay, right over here. So, and the second one is just given by this, okay, apply the Laplace transform both equations, okay. So here we use notation, we use the capital XS to denote the Laplace transform of LXT. The capital U of S is Laplace transform of U sub t. A capital Y of S is Laplace transform of Y sub t. Okay. So once we do that, we use the property. So here we use the property of a function derivative. So you can check the table to see the relation between the derivatives. The Laplace of derivatives and the Laplace of its own the original function x sub t. Okay, so it's given by s times xs minus x0. So the difference here, this is initial state. Okay, so this is a little lower case of x. This is not a bigger case. Okay, so this is the initial state. Okay, and the right hand side just directly do the Laplace transform, because this is a constant. It's just is the same as this guy moves forward, and then you apply Laplace transform to just xt, And similarly, you move this constant outside the Laplace transform of this u sub t, which is give us u sub s. Bigger u sub s is bigger x of s. Okay. Now we just have plug in, move this one. Okay, move this term to the left hand side. Of course, I also move this constant to the right hand side. Okay, so that's what's happening. So sxs minus 0, negative 1, 1, negative 2 times xs is equal to 0, 1. So here I use u sub s, u sub s because I already give the u sub t is 1. So u sub s is 1 over s. So I plug in this u sub s by 1 over s. So I have 0, 1 times 1 over s. And also don't forget we have this here, x minus x0, because minus move to right hand side become plus. So it is plus xs. So x at 0. x0 is 1, 1 right over here. So it is 1, 1. Okay. So this one can be written as time identity. So this is not an s. You cannot write an s over here because s cannot minus a matrix. So it's s time identity. This identity is here is just 1, 0, 0, 1. Okay, the identity matrix. And time xs, and I combine these two. Okay, which is 1, 1 plus 1 over s. Okay, then I put everything together. So this I take this times the inverse, right? I multiply inverse on both sides. So this xs is equal to this guy inverse times 1 and 1 plus 1 over s. Okay, which is the inverse of this guy. Okay, this whole thing, the inverse of this guy. I do this one. So this one I don't want to talk about detail, but this is how I compute the inverse of this guy. So it's 1 over determinant of the cofactors. Okay, don't forget to switch the relationship Cji, not Cij. Okay, so it's 1 over ss plus 2 plus 1. So this is the determinant of this whole matrix. Okay, this is determinant of the whole thing over here. And this is cofactors C11, this is C21, this is C12, C22 cofactors. Okay, so I don't want to write over here. And this is the remaining part is 1 and 1 plus s, 1 over s. So after some computation, we have 1 over s plus 1 squared times s plus 1 minus 1 over s and s plus 2. So which is can be written as 1 over s plus 1 minus 1 over s plus 1 squared. And s plus 2 divided s plus 1 squared. And y sub s is just to use this for what I do have over here. Y sub s is just if you do the Laplace transform, it's just 1 1 times xs and find u sub s. So this is just given by. So this is coming from here. I want to do it right over here. So this is coming. If you do this Laplace transform, you do all the way down. You get this equation. So ys is 1 1 xs plus 5 us. And since we already computed it right over here, so just replace xs by what we have computed over here. So then we have the solution here is 1 over s plus 1 minus 1 over s plus 1 squared plus s plus 1 divided by s plus 1 squared plus 5 of s. Now we find a solution of xs, ys in the s domain. Now we just have to apply the inverse Laplace transform to find the solution in the time domain. So xt is just equal to the inverse Laplace transform of x over xs. We just computed right over here. Okay, right, this is my x of s. So once we do that, we can apply the inverse Laplace transform on both entries. Okay, it's L inverse of s plus 1 minus 1 over s plus 1 squared. L inverse of s plus 2 over s plus 1 squared. Okay. Now this one linear property says the inverse Laplace transform, I can just split this two as L inverse of 1 over s plus 1 minus L inverse of s 1 over s times s plus 1 squared. The second one I split a little bit. I can write this s plus 1 as s plus 1 plus 1, so s plus 2. Okay, so this becomes 1 over s plus 1. This one divided by s plus 1 squared. So the first component is s 1 over s plus 1. The second one is 1 over s plus 1 squared. Okay. Now this one, okay, this is use the inverse Laplace transform for real and repeated poles. So the first one we can figure out the solution directly. Okay, this is straightforward. For this part, I need to use the repeated pose. Okay, if you don't know how to do it, so I had a previous video talking about how to compute the inverse Laplace transform for real and repeated pose. You can look at the videos to see how we compute. We write this how we compute the inverse Laplace transform for a form like this with real and repeated pose. Okay, so long story short, so this part can be written as L inverse of 1 over s plus L inverse minus 1 s plus 1 plus L inverse minus 1 divided by s plus 1 squared. Okay, so similar for the second one, we also have L inverse 1 over s plus 1 plus L inverse 1 over s plus 1 squared. Okay, now we can, for this guy, so we all use a table. So table for this guy is -1 and so this one, so this guy is e to the negative t. Okay, this guy is -1. Okay, so this one corresponds to -1. This guy is e minus t, and I have another one also e minus t. So there's 2 e minus t, and this guy is plus t e minus t. Okay, because this is a minus sign, and minus sign they cancel out. Okay, and this guy is e minus t, and this guy is t e minus t. Okay, so solution of xt will be just -1 plus 2 e minus t plus t e minus t, and e minus t plus t e minus t. That's the xt. So this is xt in the time domain. So once we figure the x of t, we just have to replace xt. The solution y sub t is just 1 xt plus 5 ut. Of course, you still can do this way. You can do the inverse Laplace for this guy, but it's pretty complicated. Since we already figured out the xt, so we just need to use the original relationship given by this, so which is given by y sub t is 1 xt plus 5 ut, which is 1. We replace xt by what we already computed over here, -1 plus 2 ut plus t e minus t, e minus t plus t e minus t, and 5 ut is just 1, so 5 times 1. So once do the computation, -1 plus 2 e minus t plus t minus t plus e minus t plus t e minus t plus 5. So this we can combine them is 4, and this guy will combine together will be 3 e minus t, and this guy is 2t e minus t. So that's my y sub t. So generally speaking, for the linear time invariant system, it's not very challenging to figure out the solution. Even analytical, including the analytical form, so it's already given. Okay, and also for the exact solution, okay, you can also use a direct method, use an analytical solution to find to find the exact form of the solution, or you can also use a Laplace transform, an inverse Laplace transform, to find the solution. Okay, so either way would be fine. However, for linear time invariant system, it can be challenging. So I'll talk about solution of the linear time invariant system in the next video.